Have you ever stopped to think about what's actually happening inside your phone or computer? Every time you save a photo, download an app, or stream a movie, you're tapping into this invisible, microscopic world that holds, well, pretty much our entire digital lives. But here's the thing. We're creating so much data that the engineers building this world have completely run out of space to build out. So they've had to start building up.
And I mean way up. This is the single biggest idea driving the future of memory. Forget sprawling circuits on a flat chip. Instead, companies are now stacking layers of memory cells one on top of the other, vertically, creating what you can literally think of as data skyscrapers. This whole technique is called 3D NAND, and it's the reason our devices can store more and more data without getting physically bigger. But as you can imagine, building a skyscraper that's hundreds of stories tall on a microscopic scale, well, that comes with some absolutely mind-bending engineering challenges.
And just like any real skyscraper, it all starts with a foundation, right? If you mess up the foundation, the entire structure is basically useless. It's no different in the world of 3D NAND. That foundation is just as important and maybe even more delicate.
So here's the big problem. The foundation of our data skyscraper is all the super complex control circuitry that tells the data where to go. And the process of stacking hundreds of memory layers on top of that foundation involves incredible heat and immense pressure. All that intense construction can actually fry that vital circuitry before the skyscraper is even finished. Not a great start.
For a long time, the standard method was called peripheral undercell, or PUC. You can think of it like this. You build the ground floor of a high-rise first, the utilities and shops, which are the peripherals, and then you start stacking the apartments, the memory cells, directly on top. It worked for a while, but as the towers get taller and taller, the stress on that ground floor becomes a massive, massive problem.
So how do you get around this? Well, the memory giant SK Hynix came up with a really clever new blueprint. What if you don't build the tower on the foundation at all? Instead, they use a process called hybrid bonding. They build the memory tower on one piece of silicon, and they build the control circuit foundation on a totally separate piece of silicon. Then, and this is the incredible part, they flip one over, align them with microscopic precision, and fuse them together. It's genius. No construction damage, you get a much stronger foundation, and it opens up the path to building even taller skyscrapers.
Okay, so we've got a solid foundation and a towering structure. Awesome. But now, how do you actually get data up and down hundreds of floors? You need elevator shafts, right? And drilling those is the next big engineering nightmare.
And look, we're not talking about a little 40-story building here. We are talking about structures that are already pushing past 400 layers. Just try to imagine drilling a perfectly straight elevator shaft through a 400-story building that's narrower than a single human hair.
This question really just puts it all in perspective, doesn't it? These elevator shafts are actually called memory channel holes, and they have to be carved through the entire stack with unbelievable precision, making a hole that is over 100 times deeper than it is wide, without it bending or twisting. It seems practically impossible. The old methods just weren't cutting it. They weren't fast enough, and they definitely weren't accurate enough. So what's the crazy solution? Yep, you heard that right. The answer, cooked up by the brilliant folks at Tokyo Electron, is totally counterintuitive. To etch something with incredible speed and precision, you make it unbelievably cold.
It's called cryogenic etching. By dropping the temperature way down into the cryogenic range, we're talking as cold as -70 degrees Celsius, the etching chemicals become super focused. They carve straight down like a laser, without spreading out to the sides. This lets them drill a 10 micrometer deep hole, all the way through those 400+ layers in just 33 minutes. It's a total game changer.
And get this, there's an amazing bonus. This new, super-fast cryogenic process is also way more efficient. When you compare it to the old technology, it actually reduces the global warming potential of the whole etching process by a staggering 84%. So we're building taller and faster, but also a whole lot greener.
All right, let's tackle our third and final major challenge. We've got our foundation. We've got our elevator shafts. Now we need to run the electrical wiring to every single floor. And when you have hundreds and hundreds of floors, that is a lot of wiring.
This quote from Micron Technology really just nails the problem. The traditional stuff they used for this wiring, they're called word lines, is a metal called tungsten. And for a long time it was fine. But in these new super tall, super dense skyscrapers, tungsten is like trying to use old frayed wiring. It has too much resistance, and that just slows down the flow of data.
And you can literally see the problem.
On the left, that's what happens when you use the old process to deposit tungsten. It uses this corrosive fluorine gas that actually eats away at the structure, leaving behind little gaps and defects. But on the right, you can see the new, fluorine-free process gives you a perfect, clean fill. This isn't just a minor upgrade, it's a completely different way of doing things.
So what is this magic new material? Well, Micron developed a brand new, first-of-its-kind metal just for these word lines. It had the internal code name Dogwood. And it's not just deposited with that clean, fluorine-free process we just saw. It actually has fundamentally better electrical properties than tungsten ever did.
This graph tells the whole story. It's measuring electrical resistance. That red line is the old tungsten, and the blue line is the new dogwood material. See how that blue line is consistently lower? It's that simple. Lower resistance means data moves faster and uses less energy. Dogwood is the high-performance wiring that these new data skyscrapers absolutely need.
So, with these brand new foundations, new elevators, and new wiring, the construction boom is officially on. But these breakthroughs didn't just happen in a bubble. They're all part of this intense global race to build the tallest and most powerful data skyscrapers on the planet.
I mean, just look at the scoreboard. The pace of this is just incredible. Micron is already shipping products with 276 layers. Samsung is already mass-producing chips with 290 layers. SK Hynix, like we saw, is deep into developing its 400-plus layer technology. And then you have Japan's Kioxia, which has set a goal that is just jaw-dropping.
That's right, 1,000 layers. The next frontier is a skyscraper 1,000 floors high. Kioxia thinks it can get there by 2027, and Samsung is targeting it for 2030. We're not talking about small incremental improvements anymore. This is a complete paradigm shift in what we thought was possible for storing data.
So why should you care about any of this, about these microscopic skyscrapers? Because they're the quiet foundation of your entire digital life. This race to 1,000 layers means you'll have more space on your phone for all your photos and videos. It means the gigantic open worlds and future video games will load in the blink of an eye. It's what powers the enormous data centers that are training complex AI. And it means faster, bigger, and more efficient solid-state drives in all of our computers.
Ultimately, what these invisible structures are all about is creating space, basically limitless digital space. And we've just seen the incredible human ingenuity it takes to build them taller and faster and better. So I guess the real question isn't just about how high we can build. It's as we push towards 1,000 layers and even beyond, what entirely new ideas, what new applications, what new digital worlds will we create with all of that new space?